Good morning, students. Here we are going to cover, today, we are going to cover Unit 7, Lesson 2 here, Networks and Graph. We're going to be talking about oralizing a graph here today. Yesterday we talked about how to determine if there's an Euler circuit or if there's an Euler's path. Today we're going to discuss what happens if there's not one and I want to create one. How can I go about doing that? And we do that by a process of oralization. So taking a look at the notes here. An Euler circuit, when it exists, describes the most efficient solution to any problem where tasks have to be done along the edge of the graph. So for instance, a garbage truck would be going down every street representing edges, would want to go down every edge. The mailman would want to go down every edge or every road. And the same thing with like someone who does street sweeping or anything of that nature. But many graphs don't have an Euler circuit. So what are we going to do? So if I look at this, if these are the streets here of the neighborhood or whatever it is, and I'm picking up trash along these streets, I notice this is not, and there's no Euler circuit or Euler's path here, so I can't just go down every street exactly one time, okay, without backtracking. So now the question becomes, what would be the most efficient way uh, um, to go down every street with backtracking the least amount of times, where I would have an Euler circuit. So what if we need to have an Euler circuit, but we can't because there are too many vertices with odd degrees? Well, in this case, what we'll be doing is oralization. This is the process of duplicating, this is underlined for you, edges to make all vertices an even degree. So in the last one here, we saw that all the vertices are odd. I need to make them even in order to have an Euler circuit. So we're going to oralize this graph, meaning duplicate edges or backtrack down some of these edges. That would be the practical application there. An edge must already exist or must already be present in order to duplicate. So I can't construct just some edge at random. I can't just, okay, I'll fix this real quick. We're going to go from here to here. I can't do that because I'm not duplicating an edge. I'm creating a new one here. So that would not be good. Whereas I can maybe, so I can erase this, there it goes. Possibly, here's an edge here. I could duplicate it and draw, and this edge here is a duplication. So make sure you're duplicating edge and not creating new edges. That's the #1 rule, and a lot of students get tripped up on that. All right, so what this would look like here. Which streets would you travel down twice or duplicate? So maybe, if you remember, so maybe I'm going to duplicate this street right here. I'm going to backtrack on this street. Remember, they were 3. Now, if you notice here, the degree of those edges are now 4 because I duplicated. Now there's 4 edges. 1, 2, 3, 4. There was 3, and now there's 4. Same thing over here. When I duplicated this edge here, this vertex right here, it had a degree of 3, but now it has a degree of 4. So that is the process of turning all the vertices into an even degree. Remember, these other 4 vertices are also odd or 3 as well. So this is what I did. I duplicated this edge right here, so I just drew in another one because it already exists, and so that made this vertex here go from a degree of 3 to a degree of 4. 1, 2, 3, 4. Same thing with this side here. This became had a degree of 3, now it has a degree of 4. When I duplicated this bottom edge here. 1, 2, 3, 4. I did the same, I mirrored that same thing on the other side here as well. I duplicated this edge here, and so I drew in that one, and it changed this these two vertices that had a degree of 3 now have a degree of 4. Now all my vertices have a degree of 4, hence I have oralized the graph. And I can travel down, I can start anywhere, I can start right here, and I can travel down every street exactly once and get back to where I started. Okay, I won't actually do it, but you get the point. Must already connect two vertices. The red edges indicate the duplicated edges used to turn all degrees even. I would like you, when doing the assignment today, to make sure you're using a different color when you do duplicate an edge. So if you have a blue pen, or if you have some matte pencils, please use those to be duplicating the edges. All right, next. Let's actually go into this a little bit further here. I know that was a real fast exercise there, or example. Let's slow it down and give you a few more examples, so hopefully by the end of this lesson, you should be able to oralize any kind of graph out there. So the steps to oralizing a graph. To oralize a graph, identify all the odd vertices. If all are even, we're done. Remember, an Euler circuit is when every vertex is even. That's the goal. So if they're already all even, I don't need to do anything. So we're going to identify all odd vertices. We're going to find pairs of odd vertices and try to connect them with the shortest path, the least number of edges. I don't want to I want to make sure I have the most optimal circuit here. I don't want to duplicate too many. I want to duplicate the fewest amount that I need to. And that'll make sense later on. The optimal oralization is equal to the number of odd vertices divided by 2. This is the best possible option, but it may not always be possible. So if I only have 2 odd vertices, then the optimal oralization would be 2 divided by 2, or just duplicating one edge. Sometimes that is possible, sometimes that is not. You want to try to get the most optimal, but note sometimes you're not able to. And we'll see some in example later on. Actual oralization is how many edges did you actually duplicate in order to connect all the odd pairs. So I want to connect all the odd pairs. How many did it take? How many times did I have to duplicate an edge? Or backtrack, you might say. Alright, here we go. We're going to be looking at this problem right here. And the goal is to have all even degrees. So first, let's find the degree of every vertex. Alright, so A here has a degree of 2. That's good. Don't have to worry about that. B has a degree of 3. 1, 2, 3. E has a degree of 3 as well. 1, 2, 3. C has a degree, or D has a degree of 2, and C has a degree of 2. So the only two I have to worry about are B and E. These I want to pair up. I want to pair these up. So ultimately, the best case scenario is I have 2 odd vertices. We're going to divide that by 2, so the optimal oralization will be just one edge. We'll get to that one in a sec, but just be one edge. Now, can I oralize this graph with just one edge, duplicating one edge? In this case, yeah, it's pretty easy. All I got to do is I'm going to take this edge that connects B and E and duplicate it, just like this. Whoop, there. So I didn't create a new edge. All I'm doing is duplicating it, representing I've got to backtrack along this path here. So now the degree of B is not 1, 2, 3 anymore. Now it's 1, 2, 3, 4. And the degree of E is not 3, it is 1, 2, 3, 4. So now I have all even degrees, and so hence I have an Orlais circuit. And this can be represented pretty easy. If I start at A, I should be able to get back to A. 1, boom, boom, boom. Oh, I went too far. Let's try again. 1, 2, 3, 4, 5, 6, 7. Bam, did it. Without this duplication, or without backtracking on this edge here, that would not be possible. So the actual number of edges I had to duplicate was 1 edge. Alright, so now let's look at 3 examples here, and hopefully as I go through these examples, you should be good to go on the assignment today. Again, when you, as you do the assignment, if you will duplicate the edges in a different color, it'll help visualize it for you better and for me as I go through these papers and grade them. So here's the first example here, like this M kind of thing. Let's find the degree of every vertex. So A is at 3, has a degree of 3. B has a degree of 1, 2, 3. E has a degree of 1. C has a degree of 2. D has a degree of 1. Alright, so if you notice here we have 1, 2, 3, 4 odd vertices. And so that means the optimal edges is the number of odd vertices divided by 2. I have 4 divided by 2 equals 2. Right? Ultimately, if I just want to try to do it in 2, but only duplicate 2 edges. Now, here we go. Let's see if this, what I can do here, and go through a couple pointers here. You don't need to connect all the odd vertices like this. I don't want you to do this. We don't have to connect all the odd vertices, all 4 odd vertices. That's not the goal. The goal is to connect pairs. Once you pair them up, you want to be able to pair them up. So I could pair 3 over here to this here. I could do that. So I paired this 3 to that 3. So that therefore this becomes even. This would be 4, and this would be 4. Hey, that's great news for me. The problem with that, though, is if I duplicate this edge, that's great. I paired these up. Now I got to pair these 2 up. Well, that's going to be a little bit tricky here, trying to pair those up, because I could do it this way. Well, or can I do this way? Nope, I can't. Right? Why can't I just pair them up like that? Because there's no existing edge there already. There's no road there. I can't backtrack on this path here. So that would not be possible. So this is where things get a little tricky. You have to think kind of a little bit critical here and figure out how to pair up. I want to try to get 2 pairs here in the most optimal way. And the way you can do that is we're going to pair this 3 to A to D, so those 2, and so this becomes 4, and the D here now has a degree of 2. And over here I'm going to pair them this side up, just like that. Now this B becomes 4, and that E becomes 2. So the actual number of edges I duplicated was 2 edges. Alright, moving on to the second one. So we have A, B, C. So we're going to find the degrees of each one, starting with A here. A has a degree of 2. B has a degree of 1, 2, 3. C has a degree of 2. E has a degree of 2. And D has a degree of 1. So, and C has a degree of 2 here. So looking at my odd vertices, here's B and D are my 2 odd vertices. So ultimately, 2 divided by 2, I just want to duplicate 1 edge. Okay, ultimately, I got to pair this 3 up to that 1. Well, unfortunately though, I can't just do this, because there's not an edge going from B to D to be duplicated. So I can't do that. So what am I going to do? I'm going to try to find the shortest path from B to D. On this case, I would have to duplicate B to F. I would duplicate this edge first. Then I'm trying to make my way down here to D. 2, duplicate that edge. And then finally, right here. That's what it would look like. So now I paired B, which had a degree of 3, all the way up to D, and this is the only way you can do that. So it didn't take just I couldn't just do it in one. I couldn't just duplicate one edge. I had to duplicate 1, 2, 3 edges to get this job done, or backtrack down 3 rows. Oh, I should have done that way. So when I duplicated these 3 edges here, B now has a degree of 1, 2, 3, 4. So let's see what happens. This has 4. You may be worried about F. You didn't want to change F's degree, but notice here it's 1, 2, 3, 4. Now it doesn't have a degree of 2 anymore. It has a degree of 4, which is still even, which was what I want. Next is E, and E also has a degree of 1, 2, 3, 4. So that's good. And then D now has a degree of 2. And so there's the oralized graph. So ultimal edges was 1, but it actually took me 3 edges to get the job done. Okay. Sometimes you will, you can get the ultimal number of edges. Sometimes that's not the case. It may take you more. All right. Now we move on to the last one, this box. So let's find the degree of every vertex. B has a degree of 3, A has a degree of 2, D has a degree of 3, G has a degree of 2, F has a degree of 3, E has a degree of 2, and C has a degree of 3. So let's see how many odd vertices there are. Looks like there's 4 of them. We got B, C, D, and E. So ultimately, I want to try to get it oralize a graph with just 2 edges. Can I actually do that? Well, let's see. And again, you're not trying to connect all these 3's up. You want to pair them up. So let's start here with something pretty easy. Let's just duplicate this edge. I want to pair these 2 up here. 1, 2. So once I did that, that has a degree of 4, and this has a degree of 4, and I'm done with that pair. Again, we're not trying to connect them all the odd vertices. We're just trying to pair them up with an edge. So there's 1, done with that. So now I want to pair this D up to this E right here. And you can do it several ways here. Notice they're not just 1 step away. It's not just, I can't draw in an edge going from D to F because there's not one there to duplicate. I'm going to have to take a couple steps, but I want to keep in mind I want to do the fewest number of edges. Okay? So the way I did it is I went from D to G, and then I went from G to F. So that's how I got this pair to connect. So with that, D now has a degree of 4. G has a degree of 4 because it went from 2 to 4 now. And then F also has a degree of 4. Hence, the actual number of edges I had to duplicate was 3 edges. Alright, that's the end of oralizing a graph here. Hopefully Sub will give you the assignment. Go ahead and see how many of those graphs there you can oralize. I think the graph is, there's the assignment right here. There's the back page, in which you will do answer those questions there. Okay, so have fun. I'll see you guys Tuesday.